Hello everyone, welcome to my channel. My name is RF and today we're going to talk about KVL and KCL more complex problems. So we're going to specifically solve a more complex problem using both KVL and KCL analysis. Here is the circuit that I'm trying to solve today using both KVL and KCL analysis modes. So let's start with KCL, which you might know it as node analysis. So I say KCL or node analysis. In KCL, we know that we have to first point out to some critical points, or we know them as nodes. So which one of these nodes would be my critical node? Can I say that this node here is my critical node? So the answer is no. And the reason is that this node is a continuous 8 amp going to and coming out of the node. What about this node here? Is this a critical node? Again, the answer is no, because as you can see, this 8 amp flows into this node and out of this node. But if I were to choose this one, let's call it node A, and this node over here, let's call this node node B. I can say these are critical nodes because they do look like an intersection. There are 3 different currents going in or coming out of this node. So if I consider this 8 amp and I follow the route of this 8 amp, it looks like this is where the 8 amp coming from. So I can say that 8 amp just going out of this node. And also I have a dependent voltage source and the value is 4I. So I don't know the current of this dependent source. I just call it I. Let's just call it I. Or I call it I1. And also this node, I don't know the current either. So I just call the current of this branch I2. So I don't know the currents I1 and I2. I'm going to just solve this node first. So let's solve the equation at KCL of node B. If I want to write the KCL at node B, and if you guys remember from the previous sessions, we said that always consider the direction of current as going out by default. We consider the direction of current as going out being positive. So if I consider like I1, as you can see, it's going out of node B, so I consider I1 as positive. And same story for I2 plus I2. Do we have a negative current? No, because 8 amp is also going out of node B. So plus 8 equals 0. Let's just keep this equation in mind and call it equation 1. Continuing with this circuit, I have also node A. So let's write KCL at node A. What I get here is again this I1 that we're going out of node B. If I follow the path, I reach node A. So I1 goes into node A. So if I look at the direction of current, going out is positive and going in is negative. So I1 is going into node A. So I can say minus I1. On the other hand, I have a 2 amp. As you can see, this is a diagonal branch that originates from the bottom left corner going all the way to the top right corner of this loop over here. So I can say minus I1 minus 2 amp. What else? this one going out of node A, so I call it positive I, equals 0. So I have I minus I1 equals 2. I also have I1 plus I2 plus 8 equals 0. As you guys can see, there are two equations, but we have three unknowns, I1, I2, and I. I need to figure out one more equation, or I need to just find the real value of one of these three unknowns. I have three variables, but only two equations. What else? If you look closely at this circuit, there's another critical point, which is this point here. Is it worth writing a KCL at this node? The answer is yes, but I don't want to write the KCL just now. If I consider this node as my potential reference, if you guys remember, the potential reference is where the voltage is 0. So I consider this point at the bottom right as the potential reference of my circuit. So the voltage of this point is 0. I have this 10 volt source. It shows that this point over here, this node, if I were to write the voltage of this node, it's 10 volts. Why? Because the reference point is right across this voltage source. So if this negative polarity is 0 volt, this positive polarity has to be 10 volt over here. So I know that this voltage is 10 volt. Let's look at this voltage here. The voltage of node B. If you follow the path, the voltage of node B is positive 4I. Yeah, we should follow the path towards the ground, So positive 4I, and over here I have positive 3I, and then this is ground, right? So the voltage of node B is positive 4I plus positive 3I, which is 7I. So 7I is the voltage of node B. I also know that the voltage of this node here is 10 volts. Why am I interested in voltage of these two nodes? You're right. I want to figure out current I2 over here. So we know from Ohm's law that current is nothing but voltage over resistance. I equals V over R. So let me just go a little bit down. I know from Ohm's law that I equals V over R. So from here, what I want is to figure out the the current of this branch over here, which is I2. So what is the voltage of this branch? It's the voltage of this node, node B, which is 7I over here, minus the voltage of the tail, which is 10 volts. So 7I minus 10 is the voltage divided by 2. So 7I minus 10 divided by 2. This is the voltage of, this is the current I2. This current, the current of this branch here. There you go. I have one more equation now. So from here, I can find the relationship between I and I2. So 2 times I2 equals 7I minus 10. Or I can say I2 equals 7 over 2 is 3.5 I minus 5. This is equation number 3. Now, look at this equation number 1. I have I1 plus I2 plus 8 equals 0. And I have I minus I1 equals 2. And there's another relationship between I2 and I. So let's substitute this one into equation 1. So we have I1 plus I2. Instead of I2, I want to write 3.5 times I minus 5. And then plus 8 equals 0. So from here, I have I1 plus 3.5 times I minus 5 plus 8 is plus 3. And if it goes to the right hand side, it becomes negative 3. So now, this is equation 4. I want to compare these two equations. I have two equations, two unknowns, I and I1. So I should be able to solve it. This is positive I1, this is negative I1. All I want to do is just to add these two equations. If I simply add these two equations, it becomes I minus I1 plus I1 plus 3.5 times I equals 2 minus 3, which is minus 1. So I1, negative I1, positive I1 cancel out. I plus 3.5 times I is 4.5 times I equals negative 1. So from here, I, which is what we were looking for, is minus 1 over 4.5. You may not like I write it this way. Let me just clean it up. I can say I equals, if I multiply numerator and the numerator and denominator by 2, I get minus 2 over 9. But in any circuit, the unknowns of the circuit is usually the voltage of the nodes. So what I want is the voltage of node B and the voltage of node A. Now that I know I equals minus 2 over 9, I can easily say the voltage of node B and node A. So from here, the voltage of node B is 4 times I, which is minus 8 over 9, plus 3 times I. So that becomes minus 6 over 9. That becomes minus 15 over 9. So if I just divide them by 3, it becomes minus 5 over 3. That's the voltage of node B. What about the voltage of node A? That's easy, just 3 times I. The voltage of node A is negative 6 over 9. Or if I divide them by 3, it becomes negative 2 over 3. So I hope you guys enjoyed solving this problem, and I hope that you all got the answer right. Thank you for your time, and we will solve more of these problems in future. And next session, we will most probably continue with Thevenin and Norton theorems. Thank you again. Please, if you liked the contents that I provided, don't forget to like and share my channel, and let's help everyone grow together. Thank you very much. Have a good day.